Welcome everyone to the first of two sessions we're having in succession in this room on emerging ideas at ARPA-E. The purpose of this session is to really open the funnel wide, give you a peek under the hood of some big new ideas that we're currently in the early stages of exploring, and also to get your ideas for areas that we should consider. I want this to be, part of the ARPA-E spirit, part of the culture is the value of constructive confrontation. So I'm hoping this will be a fun, active session, maybe one notch below British Parliament. My name is David Danielson. I am a Program Director at ARPA-E and the nominee to be the next Assistant Secretary for Energy Efficiency and Renewable Energy. And to my right are four of ARPA-E's fellows. So the ARPA-E Fellows Program consists of some of the best and brightest recently minted PhDs, and we use this group as an incubator for new ideas. Whenever anyone in the organization has a big, hairy new idea, we throw it into this cauldron, and the fellows bounce it around, work on it, reach out to the community, and try to figure out whether there might be something there. And so the way this panel is going to go is that each of the fellows here are going to give a 6-minute quick pitch on an idea that they've been working on. I want to remind you that these are very embryonic, very early ideas. If these end up getting traction, then some subset of these ideas will have workshops run around them, and then perhaps a subset of those would actually result in an ARPA-E program. And so the way we're going to run this, like I said, we're going to do 4 quick pitches, and then we're going to open up to questions, comments, ideas from the audience for about 15 minutes on these specific quick pitches. You'll have an opportunity to speak at the mic, or we also have on the chairs around you note cards, or if you can write at the top of the note card the program that you're interested in commenting on, and then very clearly and legibly write your question or comment. We'll be collecting those, and I'll be introducing some of those questions as well. And then the last 15 minutes or so, just want to open it wide open and have you, the audience, stand up and give us some of your ideas for areas that you think that ARPA-E should be considering where we haven't done work yet. And with that, I'll pass it over to the ARPA-E fellows for their quick pitches.
Good morning, everyone. My name is Amul Tevar. Thanks for coming to the Emerging Ideas session. I think the best session that we'll have here. It's the most interesting for sure. I am an ARPA-E fellow. I got my PhD in Material Science and Engineering from Carnegie Mellon University. And today I'm going to be talking to you about something we've been thinking about, which is rapid EV charging. Now, to frame the question, how many of you here own a purely electric vehicle or are seriously considering it for your next vehicle? All right. Now, our goal is to get a response from everyone across the United States that we can make EVs as convenient as traditional vehicles. And a major barrier, besides range, besides cost, is the charging. Charging takes a significant amount of time, and most consumers are not willing really to wait that long, or it's a turnoff from actually, when it comes to the point of sale, purchasing an electric vehicle. So our goal at ARPA-E, and the question I'm kind of asking is there a way that we could make EV charging as convenient or more convenient than traditional systems? Most existing lithium-ion batteries for EVs, these are just a sample, take about 3.5 hours to charge to 80 or 100%. There are some newer systems coming out or that are already out that have about a 30-minute charge rate, with the caveat that this will reduce your long-term battery life. This is a small problem if you consider that you're already paying a little bit more up front for your EV to then have that convenience for the fast charge take out for your battery life. That's something we want to address. So a global study looked across the world, and for the United States found that the maximum time people are willing to wait for charging is about 2 hours. We want to get that down to 10 minutes. That said, we realize that this is a very complex problem because you're taking something that normally takes 3 hours, 2 hours, and compressing down to 10 minutes, things that might have been minor secondary issues for larger packs and slower times suddenly become very relevant, from thermal management to communication between the battery pack, the charger, the battery pack to charging utility even, because whereas before you're talking about a little bit of energy over a long period of time, now you're asking to have that 2 hours of energy in one short burst. And so as we're kind of looking at the problem, we're coming up with ideas. Are there ways that we could circumvent some of these fundamental issues? Are there technologies or possibilities of things that could work to kind of address the idea of rapid charging? So a common idea is you use your battery in your EV, you pull up to a battery replacement station, you swap out your battery and you go on your way. But why swap out the current collectors, your power electronics, the whole system? What if you could just swap out the used part of the battery? So that kind of leads us to the idea of, could we look at a flow battery? Could you go into a station, pump out the used electrolyte, and pump in fresh stations and go on your way? And then we kind of floated the idea, well, instead of 2 pipes, 1 for each electrolyte, what if you could just have 1? What if you could have a self-assembled battery? There's been a lot of work making mesomaterials that actually have functional electronics after self-assembly. What if you could have an EV for about 7 years and you decide, you know what, there's a new battery chemistry that came out, I want to get it. And you could go to the station, pump out your old battery, and pump in a new one through 1 pipe, and about an hour later have it self-assemble and you go on your way. And this kind of leads to, why are we looking at rapid charging? Why do we think it's so important? Well, one is we want to make sure that we can make EVs as convenient. And for that, we could have something like a rapid charge station. You pull in something that's outside of your own home, so you don't have to worry about the cost of the actual at-home unit. You charge, you get a cup of coffee, you go, and you're on your way just like a gas station. But if you have the ability to rapid charge, why limit yourself to just what you can do with, a pipe or, using a wire? What if you could have wireless charging? Could we address this in a way that you wouldn't have to necessarily stop the car to charge? There's been success with inductive and wireless charging. What if you could drive over a strip of the road and have it charge your car while you go and then you take off on your way? Do we need, if we're using these radical systems, can we fully exploit the entirety of it? And so we don't know what this system may look like. We have a lot of different aspects, a lot of very complex, things that we need to be taken into account. And this is where we'd love to have some input from you, either through the cards here or, finding us afterwards. Are there fundamental things that we are overlooking or that we need to make sure we take into account? But the one thing that we are pretty sure about is that a key metric is the driving miles per minute of charge. We want to be around 20 miles to 30 miles per minute of charge. That's the goal. Now, what can we do around there? What ideas are there that we could do that would allow us to get there? And we'd love to have your input on this. And to close, if this were to become a potential project, we would call it a rapid, active charging environment. RACE. Thank you very much.
Good morning, everyone. My name is Rob Conrado. I got my PhD at Cornell University in chemical engineering, and today at ARPA-E I've mainly been working in the area of transportation fuels, and today I'd like to present a deep dive I've done around future bioreactor concepts. So, no matter what your feedstock is for making biofuels, they all face similar challenges. You want to reduce the footprint, you want to increase the efficiency and capital efficiency, and you want to reduce the land and water requirements. But when you're comparing the approaches, some of those on the right have the greatest potential to overcome these challenges in ways that you can directly convert sunlight to fuel through something like algae, or ways to convert electricity into fuel, through similar methods developed at ARPA-E in a program called electrofuels. And so the thesis of this talk is really, how can we bring those latter approaches to scale in a cost-effective way? How can we get direct conversion of sunlight or electricity to fuel? And so to bring these to scale, we need fundamentally different bioreactors than what we have today, where we convert biomass or sugar into fuel. And traditional processes, ones that are biomass-based or sugar-based, are volume-based processes. And that's because the sugar is delivered into a volume and your fuel product is separated from that volume. So the only thing that you worry about is what is your reactor volume. However, conversion of sunlight or conversion of electricity to fuel is very different. Delivering sunlight or electricity, you're delivering it to a surface. The fuel product, you are then separating or concentrating from a volume. So the key consideration here, because sunlight or electricity, don't really penetrate into a reactor, is what is the surface area to volume ratio for your systems. And especially as you bring these to scale, this leads you to very different types of reactor setups. So as an example of how this is done today for photosynthetic systems, we need very large surface areas to collect the light energy. So as you can see, this leads to some very large bioreactor cartoons. And because you need the fuel to accumulate, you need to wait a really long time. And since the product streams tend to be very dilute, it makes the separation and concentration steps very challenging. And there's been a lot of focus here. And as a result, it's been very energy intensive. And I would say that there have been few designs that have been explored. There have been a couple systems that are tried, open systems, closed systems, ways to try to increase the productivity, vary some of the parameters. But as I've said, this surface area to volume ratio is a really key consideration when you're designing your system if you want cost-effective separations. And so, you can do some back-of-the-envelope calculations, say what is the surface area to volume ratios for these systems. For open pond, it's about half a square meter per meter cubed of reactor volume. Tube or sheet photoreactors, offer some advantages. But the question remains, what kinds of surface area to volume ratios do we need? And if you want to achieve commercially relevant productivities, so you don't need Herculean efforts in your separations and concentration steps, you really need surface area to volume ratios that are greater than 500 meters squared per meter cubed of reactor volume. So that's 1 to 3 orders of magnitude greater than systems we have today. So the question that I've been looking at are how can we get light and electricity into a reactor in a way that there is an enormous surface area available to these microorganisms to convert it into fuels. And so looking at some ideas from the computer industry, information technology, advances there, what if we took some cheap optical fibers, a concept that has not been explored in a long time, or what if we took some concepts related to photonic crystals, ways that we could achieve surface area to volume ratios, on the scale of 1,000 or 10,000 or even greater meters squared per meters cubed. How could we get microbial systems to grow in these systems? How can we get the lights into the reactor and available? Alternatively, for an electrofuels-based approach where you want to convert electricity into fuel, what if we look at recent advances from the materials community or the advances in battery electrodes? In these battery electrodes, in these electrochemical systems, they're already designed to achieve very high surface area to volume ratios. Can we port these over? Can we scale them up for microbial systems? Looking at battery electrodes or nickel foams, they also achieve surface areas in the order of 1,000 to 10,000. What about something like this? And while this is not yet an ARPA-E program, what I've been calling this is microbial interfaces and coatings for reactor optimization in bioenergy systems. And while microbes is a little bit of a misnomer because it's about the reactor, not the microorganism, I'm, in addition to taking your questions, I'm also happily take some suggestions on better acronyms for this program. Thank you.
Good morning. My name is Asegun Henry. I've been an ARPA-E fellow for almost a year now. Did my PhD in mechanical engineering at MIT. Then I went on to do 2 postdocs, one at Oak Ridge National Labs and one at Northwestern. And I'll be starting on the faculty at Georgia Tech in a few months. What I want to talk about today, even though my background is in heat transfer and atomistic level simulations, even though I work at the very small scale, my passion has always been really big scale energy production. And so I want to talk about power generation today. And if you think about where all our electricity comes from, most of it comes from heat engines. And we run heat engines, and those are Carnot limited. And so what we'd like to do, since it's very difficult to change the low side temperature because we're usually rejecting heat to the environment, we'd like to raise the hot side temperature as high as we can. And if you look at the history, where we started out, we used steam Rankine cycles, which operate roughly in the range of 500 C on the hot side and dissipate the heat down around 35 C. And then we developed natural gas burning air Brayton cycles, where we can get up to almost 1500 C or so, and dissipate the heat as high as sometimes as 600 C. And these two systems are, generally roughly in the range of 30 to 40% efficient. And we had a major breakthrough when we realized that we could actually stack these things on top of each other and get more efficient. So we start with to get a combined cycle, we start with a natural gas cycle, and then we dissipate the waste heat into a steam Rankine cycle and reuse it, and that gets us up to 50 to 60% efficient. But the real question is, why are we've been kind of stuck at 1500 C. Why can't we go higher? If you think about natural gas, you can actually burn it about 500 degrees hotter, about 2000 C. And that's a big issue for the power industries. You'd like to go to higher temperature, but why have we been stuck there? And when you think about it, it really comes down to this, how a heat engine works. You start from heat and you convert to mechanical energy first, and then you convert to electricity in a separate step. And it's the conversion from heat to mechanical energy is where we have the issue. Because fundamentally, going from heat to mechanical engineering to mechanical energy means that we have moving parts, and those moving parts are subjected to dynamic loads. And so if you have moving parts at really high temperatures, it's really difficult to find materials that can last and be durable for on the order of 10 years or so at those extreme temperatures and those extreme environments. So one thing we've started to think about is, can we go to higher temperatures if we think about using a cycle that doesn't have moving parts? So maybe we can go to much higher temperatures if we take away the mechanical requirement and don't have to have materials that are strong at high temperatures. They just need to remain solid. And so we've started thinking about the idea of using topping cycles, which could potentially go on top of a Brayton cycle or potentially go to a higher hot side temperature and still dissipate to a steam cycle. So it's a fun idea to think about, but what can possibly get us there? And I'm going to talk about 4 potential pathways or ideas that we've been looking at that we find quite interesting, but we imagine there may be a host of different ways to go about this. So the first one is thermally regenerative electrochemical systems. If you think about a regular battery, which I have a picture of here, it discharges, you have an active species that goes through an electrolyte, you get work out by using the electron, and then when you charge it, you apply a voltage and push the active species back through the electrolyte in the reverse direction. Another way to do this, though, is actually to use heat. And so you can actually condense the active species out into a liquid form at higher temperature, use that waste heat in a secondary cycle, so this could be thought of as a topping cycle, and then you put the active species back where it started by evaporating and putting in heat at a higher temperature. So this is one potential direction we could go, and then you could also think about thermoelectrics. In thermoelectrics, people have usually thought traditionally for waste heat recovery, and they usually have lower efficiencies below 10% or so. But to our knowledge, nobody's really thought about pushing thermoelectrics to extremely high temperatures. What that would mean is totally new classes of materials, potentially oxides, carbides, or nitrides. And I have this figure here that shows the 3 key properties that matter for thermoelectrics, which are the Cizek coefficient, electrical conductivity, and thermal conductivity. And the red graph kind of shows roughly in the middle of the carrier concentration. On the left you have insulators, on the right, on the other extreme, you have metals, and in between, what we use today, what are the best thermoelectrics, are the semiconductors, which are kind of halfway in between. But if we go to extremely high temperatures, we may actually push the dome of optimal materials actually to the left a bit. And so it might be materials that are more insulating at room temperature, but at these extreme temperatures may actually be electrically conducting enough to work as thermoelectrics. Another idea, kind of crazy but very interesting to think about, is what if we use photovoltaics at high temperature, right? So imagine a CSP plant, but instead of having the receiver and having all the energy go directly into heat, we actually put it into a PV module, and the PV module is the actual receiver, and then all of the waste heat from the PV module is able to still be used in the thermal cycle. So this would be a nice, interesting hybrid between concentrated PV and CSP. And in thinking about this, when you talk about operating PV at high temperatures, people will think you're crazy because PV efficiency generally drops very quickly with increasing temperature. However, we've talked to a number of different people, specifically NASA has actually thought about this because they have satellites that they want to take very close to the sun. And it's what we've realized is that we don't see any fundamental reason you can't operate photovoltaics at higher temperatures. I mean, there's nothing inherently special about 300K and why they work well at 300K but can't work well a few hundred degrees hotter. And so what it appears to be is that you have to re-engineer the cells so that they can actually be efficient at those temperatures. And so we're thinking that might be an interesting engineering challenge to actually engineer PV cells that can be efficient at high temperature. The last area that might be of interest is in thermionics. Now, thermionics has been looked at several times over the last several decades. But one thing that's relatively new here is that we want to think about thermionics in the context of concentrating solar. So previously, thermionics have been restricted to temperatures around 2000 C or so, where you can burn natural gas. But with solar, you can actually get to much higher temperatures, and thermionics have extremely strong dependence on the temperature. So the efficiency and power density scale almost exponentially with the temperature, with the hot side temperature. And so these devices actually become much more efficient at higher temperatures. And so we're thinking this might be also another interesting direction to look at for how to have a topping cycle in the context of concentrating solar. You still use the steam ranking cycle on the back end and still could potentially store the energy and have all those advantages, but you could potentially raise the overall system efficiency higher. So we're thinking that the goal for something like this would be to, let's push the paradigm. Let's move beyond the 60% combined cycle efficiency that you get with natural gas, and let's see if we can get higher than that. And with a lot of these devices, the main issue is their lifetime. So we want devices that can last 10 years and be reliable. So in thinking about this idea, one of the acronyms we've been using is thermodynamically optimal power from the highest achievable temperatures, or TOPHAT.
Hi, my name is Phil Rochelle. I'm a postdoctoral researcher working at ARPA-E. I have a PhD in physics from Harvard University, and I did my doctoral research at CERN, the European Center for Nuclear Research. After my PhD, I worked as an energy analyst at Lux Research Incorporated in New York, and then at an energy nonprofit here in DC. The topic I'll be discussing in this section is low-cost, high-sensitivity methane detection. So methane is the primary constituent of natural gas, and there's been a lot of interest and excitement over the past several years over the large new discoveries of domestic gas in the United States. Now, switching from coal to natural gas in the electricity sector reduces the amount of CO2 put up into the atmosphere. This is good for reducing climate change. However, methane itself is a very powerful greenhouse gas. Molecule for molecule, it's significantly more potent than carbon dioxide. This table shows the global warming potential, which is the propensity to absorb and re-radiate infrared radiation of methane and CO2, where the power of CO2 is normalized to be 1. So as you can see, the effect for methane is significantly higher. The relative potential goes down over time because methane falls out of the atmosphere more quickly than carbon dioxide does. But the key point here is that methane leaks from natural gas infrastructure can reduce or even reverse the greenhouse gas benefit, especially in the short term, of switching electricity from coal to natural gas. A couple of studies have analyzed this effect for different possible methane leakage rates. This one study from the National Center for Atmospheric Research basically shows that if you have a methane leakage rate of 10%, 5%, and so forth, that you can actually have a higher temperature change from switching to natural gas from coal out to 2050 or even 2100 until the methane has a chance to fall out of the atmosphere. Now, it's important to say that part of this effect is from the fact that you get aerosols from burning coal, and that reflects sunlight, and you don't get that from burning natural gas. But the overall message is clear and obvious, which is allowing huge amounts of methane into the atmosphere has a significant potential to raise the Earth's temperature. There's been a significant build-out of natural gas infrastructure over the past several years. There were over 3,000 shale gas wells drilled in the United States in 2010 alone. So the question is anyone checking the wells and the pipeline infrastructure for methane leaks? Do industry and government have the proper tools to find these leaks and stop them? Now, this is not only an emissions issue, it's also a case of a wasted resource, because obviously allowing a bunch of natural gas to just go off into the atmosphere is a lot of wasted money. In terms of what the status quo is for what the methane leakage rate is, data is hard to come by. But there are some instances which raise concern. In the February issue of Nature magazine, there was a story about how sensors set up outside of Denver that were actually meant to detect something else happened to find out that the nearby shale gas wells appeared to be losing as much as 4% of their methane into the atmosphere. Now, the green bar graph here shows what people had thought that the methane emissions rate should be based on industry activity, but the blue and red are what the sensors actually found. So the message here is we don't really know where these methane leaks are happening. So when we think about, kind of technology solutions that could potentially solve this problem, our key focus is to find the leaks and stop them. Now, to do this, we almost certainly have to be able to constantly measure a large geographic area. So we want ubiquitous sensing of methane concentrations in the atmosphere. We also want to be able to pinpoint, what well or what part of the pipeline the methane leak is coming from. So we want to have spatial resolutions that are below a square mile. And then finally, we need to have a detection sensitivity which is on the level of the natural abundance of methane in the atmosphere, which is about 1 part per million resolution. So in terms of technologies that can do this, and we really want to open it up to the community to see what your thoughts are, but we always start to see what the state of the art is. Now, there are a lot of methane detection techniques, both remote and local. And here you see a couple satellites from satellite-based measurements from NASA and from some European agencies. And these look at methane and CO2 concentrations across the entire globe. But they're more interested in large-scale phenomena like how much methane is leaking from the permafrost or deforestation. What we need is much better spatial resolution so we can pinpoint these leaks. So what are ways to do this? Well, as we're brainstorming, coming out of the lab, we think of something like laser spectroscopy. Here we could exploit the fact that methane in the atmosphere absorbs very specific frequencies of light. Now, one class of lasers that might be promising for this application are called quantum cascade lasers. The advantages of these lasers are, one, that they're largely semiconductor-based, so they could potentially be cheap, somewhat like diode lasers. And the second advantage is that you can make these things to have frequencies in the infrared, which is what you need to detect methane. So these kinds of lasers are already being used to detect methane for certain applications like emissions from natural gas vehicles. But the hard technical challenge is, can the detection range be extended? And this is a hard problem. Can you actually use a laser to be able to detect at hundreds of meters or even kilometers what the concentration of methane in the atmosphere is? Now, if you were to have such a laser detection technique or any kind of remote sensing technique, you can imagine doing something like mounting that on a plane or even an unmanned aerial vehicle. And then if you want to have a good signal, what you could do is you could have that laser being caught to a detector somewhere on the ground. Now, you could also do a backscatter experiment, but there your signal wouldn't quite be as good. So the idea is you have a ground-based detector, a laser in the air, or vice versa, and you can have the drone move around intelligently to be able to triangulate where the methane leak is happening. Another possibility is you could have plane-to-plane or drone-to-drone detection so that you could have more intelligent kind of dynamic moving to find where these leaks might be happening. And now, on the last slide, I showed an example of a drone or a UAV, which was the Predator, which, if you've ever seen one, is actually quite big. But there's no reason that the drone has to be that big. New kinds of UAVs are coming out, such as these things called quad rotors, which are really neat. And they can be made small on the order of tens of centimeters. And so if you have a bunch of these things and they're really cheap, you can imagine outfitting them either with remote sensing or even cheaper local sensing. And the point is that they intelligently coordinate between swarms of these things, and they sniff out and move intelligently to be able to follow concentration gradients and find where the methane leak might be happening. Now, one challenge is how to power these things, and we've had some fun thinking about this. One way might be to have a solar panel on it, and it just recharges and operates whenever it can. But another thing that we think would be really wild would be if these things can actually recharge on power lines. Now, if we want to go really crazy, if we go even smaller, we can take this drone concept and keep shrinking it, and then you get to this idea of what's been called smart dust. And this is really out there, but the idea is that if you have sensors that are small enough and cheap enough and have embedded communication capability, you could just put these things everywhere. And then, we can think of other sensing applications, right? If we develop this for methane detection or whatever, we can start to think, what are the other sensing things that we can do which are going to be beneficial to the energy space? And then one last question is, can we crowdsource it? There are very cheap local methane sensors which are available. You can buy these things for dollars. So what if we were to equip these things with some kind of Bluetooth capability so that the sensor can talk to your iPhone or your Android, and then you have an app which then kind of uploads that to the internet, and some central detective is using these concentration gradients to find out where these leaks might be happening. So this is not a program and may never be, but if it were, we thought that a fun name for it might be sensors and networks integrated for finding emissions remotely, or sniffer. Thank you.
All right, well now it's your turn, audience, to engage the panel, to give them questions, comments, feedback on these specific ideas. To remind you, we have 4 ideas on the table here. The PACE idea about rapid charging in EVs, the microbes concept about advanced bioreactors, top hat on advanced high-temperature thermodynamic topping cycles, and sniffer, I think is my favorite name, on methane detection. So what I'd like you to do is, you all have cards, so if you have questions or comments that you'd like to just have sent up to me that then I can use as part of the moderation of this panel, you can send those up relating to these ideas. In addition, if you have some specific new ideas that you think ARPA-E is missing or should consider that are in areas where we haven't done anything yet, please feel free to put those in on the card as well. And I'd also like to invite you to go to the mics, but just for fun and to put the fellows on the spot, I thought it might be fun to take a vote. Which of these ideas do you think represents the highest impact ARPA-E program? And you can just raise your hand to indicate which is your favorite. So the PACE program, fast charge. Pretty good. Microbes, bioreactors. Top hat, topping cycles. And sniffer. All right, well, it looks like fast charge and the topping cycles are at the top of the list. Let me give you about a minute to throw out your question or comment for the panel.
Thank you. Guy Lay from Intel Labs. 2 comments. First on the rapid charging. Direct current level 3 charging already meets your 20-minute requirement. I understand you can charge a commercial truck-sized vehicle to 60% in 15 minutes and full charge in 30. But have you considered ultracaps that you could probably charge in less than a minute? And then the second thing on the ubiquitous methane sensing, Department of Homeland Security is already looking at nuke and chemical sensors. Why aren't you teaming with them to put these on emergency vehicles? So those really aren't questions, they're comments.
So in terms of the level 3 charging, the Nissan Leaf has a level 3 charger, but they haven't yet reached a decision on which type of level 3 charger will be the final version, because they have an issue with some of the communication ports, that because you're rapidly charging these batteries, you want to be able to communicate between the charger and the battery pack. The systems I think you're talking about for the fast charging in trucks, those are lithium titanium oxide based, and they have a lower energy than what could be used in a light duty vehicle. Otherwise they would be absolutely there. And so the charger's there, that's power electronics, that's there. But a system that can then fast charge over thousands of times does not, as far as I'm aware, is not there yet. Well, for a light duty vehicle.
Yeah, that's why I say ultracaps, because they avoid the whole electrochemical.
And if there's an ultracap with, I think, enough energy, then yeah, absolutely, that would take care of the issue.
Okay.
Quickly on the methane sensing, we're in the early stages of this, so we've reached out to other government agencies such as the EPA, but you're absolutely right. We should be seeing what Homeland Security is doing and seeing if there's some coordination that's possible.
That's great. Over here.
Good morning. I'm Michael Flickinger from North Carolina State University, and this is a question from Roberto. In considering your 2 materials, the optical fibers and photonic crystals, have you looked at the capital cost of those? Because I believe that's going to be one of the main things for large-scale absorbers.
So I think the capital cost is a key consideration here, and the system that I'm looking at is not a low-cost, low-efficiency system, but a high-cost, high-efficiency system. So a critical question is how much power can you pump through these devices? And I think that if you can deliver sufficient power at high efficiency, then that upfront capital cost may not affect the final fuel price significantly. But it is something that I've been thinking about in developing this concept.
And do you consider microbial coatings on these devices? I wasn't clear from your presentation.
Yeah, that is something that have been discussing. I think it's important to figure out a way to get the microorganisms to stay stable on these surfaces, and make sure that they grow. Is there a way to encourage biofilm formation on them?
Okay, you may be aware that I'm the inventor of microbial paints and inks, and we've recently achieved some of the same results you speculate by coating papers. The advantage of papers is we have a paper coating industry, and we can coat paper very fast. So I think you should consider some alternative supports for thin coatings. It might be useful.
Certainly. I'd be happy to follow up.
Great. And just to remind you, the questions that you're writing down on your cards, please just pass them in the middle, and we'll have folks pick them up. Here in the middle.
I think my name is Ed Pyle. I think the electric vehicle rapid charging is some of the ideas that were already in there were already good. I'm not sure that we actually need to go to the fast charging. I think the cartridge idea, making standardization in industry to certain cartridge sizes and maybe multiple cartridge sizes so you can plug into different total power requirements in different vehicles is already possible. And then use slow charging at the gas station, so to speak, and stuff to do that. And that already can be done today. It just requires going to industry and trying to get agreement on some standard form factors for that. Right. And one other one, and I'll step back, is for the topping cycles and stuff like that. I think thermophotovoltaics can already be done today as a topping cycle at very high temperatures, because the photovoltaics are actually at low temperature when you do that, but they like high temperatures for higher efficiencies.
Thank you. Any response to those comments from the panel?
Yeah, I absolutely agree. I mean, if there could be a standardization that would take care of a lot of the battery charging issues. When we were talking to some of the experts, their basic idea was good luck, because getting a German company to put in the same, form factor as a Japanese company would be kind of difficult, to then have that also be the same for the U.S. company. But if that could be done, absolutely, that would take care of the problem.
With regard to thermal photovoltaics, you're absolutely right. That's another potential technology that would be interesting. In comparing it to the idea of running PV at high temperature versus thermal photovoltaics, the way I understand thermal photovoltaics, you're basically, in a way you could look at it as downgrading the heat, because you would be taking the sun, concentrating it, and then having some emitter which is now at high temperature but much lower temperature than the sun. And so TH in your Carnot efficiency would be the temperature of the emitter, now emitting to a specific PV cell which is now operating closer to room temperature, just to take in that re-radiation from the emitter. And so instead of having the intermediary to basically have it as a filter, it basically serves as an optical filter so that you get the energy in a spectrum that you like for your PV cell. This is kind of an idea just to think about using PV at higher temperature, just so that you can make use of all the waste heat, so you can still use it at high temperature and potentially store it and use it in a CSP infrastructure as they've already developed.
I was just thinking of a topping cycle on some kind of chemical or gas-fired system. And then you could use it at very high temperatures because there's no moving parts. I think as far as the electric vehicle charging, you still have to standardize the charging systems and stuff.
Yeah.
Now, I admit that standardizing a large volume compared to a small volume thing is harder. So I understand that's a bigger challenge.
Yeah, but if it could be done, you're absolutely right. It would take care of, I think, a lot of it.
Great. I'm going to read a couple comments from the audience on sniffer. Do you consider methane leaks that come as a byproduct of ventilating coal seams in mines, is that a significant contributor to this? And second, I wanted to read for you is, have you thought of biosensors, microbes or plants, to detect the methane?
Great questions both. The first thing for coal methane, I should say that the study that I showed you from the National Center for Atmospheric Research does take that into account in terms of the natural gas and coal transition. In terms of sensing those out, I think that we should be able to use whatever we develop to detect methane leaks, whether they be from coal seams, natural gas, permafrost, or even cows. So this is a way to just understand where the methane leaks are happening. In terms of the biosensors, I haven't had a chance to look into that yet. I'm very interested. The one thing that I would say is that, we're also very interested in things that can be remote. So that's one of the appeal of lasers, is the idea that you might be able to sense over a larger area. But in terms of biosensors, if those can be made to have a high sensitivity and the key is be cheap and durable, then yeah, I think that that's definitely an area to explore.
On the left here.
Thanks. I'm Jenny Gerby from Dow Corning, and I have a question about the methane sensing. I can understand, excuse me, in the other three opportunities what a possible path to market would be, or how a company would make some money on something like that. In terms of methane sensing, can you comment on what a path to market would be for that, and how much money you think a company could save by using that, or do you think this is going to be more of a policy-driven type of thing?
Thank you for your question. I guess that starts to be out of our wheelhouse a bit. You know, policymakers decide what regulations are appropriate. If we're dreaming big, 4% of your methane emissions is a lot of money, and it's all profit, right? Because that's off the top. So our hope would be is that if we can make these things cheap enough, the industry will either do it for profit motives or just because it's the right thing to do. So I can't really comment on the regulations. Obviously, regulations would help move this along, but we want to develop technology solutions that can work in a number of scenarios.
Have you looked in terms of seeing how much money that would be if you say you could put it from 4% down to 1%? Do you have an idea of what that market would be?
Oh, boy, a lot. But no, we haven't looked.
Okay, thank you.
Great. I'm going to take a question from the no card here on microbes. If microbes delivers scalable bioreactors with high surface area to volume ratios, will microbial systems be able to utilize them? For example, is photo inhibition a problem for algae? Is concentration polarization a problem for biofilm-based electrodes? Have you thought about some of these fundamental limitations?
I have thought somewhat about these fundamental limitations. Thank you for your question, and I'd be happy to follow up. This is somewhat nuanced. Just because you achieve high surface area to volume ratios doesn't mean that you need to deliver power at very high densities. If you're able to achieve very high surface areas, you could imagine delivering the light at lower fluxes, which might enable you to achieve much higher efficiency conversion of that light. Now, there's a clear trade-off with cost. As for the second part of the question, Dave?
So it was about the limitations, photo inhibition problem for algae and concentration polarization problems for biofilm-based electrodes.
I have not thought about the problem with polarization, but I'd be happy to discuss further. Thank you.
Great, and let's continue with these questions, but I would also want to invite you up now for the next 15 minutes. We're open to, if you want to throw out ideas, areas that you think ARPA-E should be looking at that it's not, then we'd like to open up that part of the discussion too, but in the middle here.
My name is Shay Savipur. This is a message. This is a comment or a question for Dr. Henry. I realize you're applying basic science for power generation, but with your background, also apply this for heat transfer in buildings. Burning gas at 2,000 degrees to make our skin feel 88 degrees or 90 degrees is very wasteful, and buildings consume 47% of the energy. So apply your science to building technology also, please.
I think that's an excellent idea, and I agree completely.
We're here at the right.
Good morning. I'm Mike Hart. I'm with Sierra Energy. We're commercializing a new sort of universal gasification technology. My comment is on the sniffer concept. I'd like to point out a potential significant source of revenue to drive your model, and that is that while there are 2,300 landfills in the United States right now that are a significant source of methane, EPA WARM model indicates that at best they're recovering 20% of the lifetime methane created. Every ton of waste going in creates about 1 ton of greenhouse-causing gases. The real challenge is there are 50,000 closed landfills that are unregulated all over this country that are not only leaking into the groundwater, but also leaking methane into the atmosphere. And if those can be identified, we have a really great technology that can actually recover the waste out of the landfill profitably and recycle it completely. So we'd be encouraged if you could find something like, if you could actually identify all those closed landfills that are still leaking. Thank you.
Great. Thank you for your comment. And that's great to hear of another application. So excited to see what you're doing, and hopefully there could be a synergy and that these technologies can enable other things to come forward as well.
On the left here.
Hi, Dave.
Hi.
Bruce Anderson, Wilson Solar Power. We're developing a concentrated solar power system to operate 24/7 as a baseload plant, and we're targeting 6 cents a kilowatt hour. My question is related to that, but it's also related to many other technologies that burn fuel, and that is, and maybe this is to Dr. Henry, I'm not sure, but to what extent is ARPA-E looking at converting low-grade heat to electricity? Whether bottoming cycles, combustion in buildings, as the prior questioner asked, waste heat from our current fleet of vehicles, a lot of sources of low-grade heat.
Well, thank you for your comment. That's an excellent point, and it is something that we're interested in, for sure.
In the middle?
David Karabandikov with the Institute for Village Resiliency. In Alaska, we have 187 villages that are standalone power systems, and usually the cost of electrical production is via diesel at around 50 cents a kilowatt hour. And so these standalone power systems could serve as a strategic niche, I think, for deploying these technologies that, if they're modular and scalable, could be applied to an islanded power system situation and then scaled up to grid-sized systems. I'd like to see ARPA-E have some involvement in how to use these islanded systems, because there's 200 in Alaska, 1,000 in the Pacific Rim, 2,000 in Russia. There should be enough to get traction on a commercialization scale.
Yeah, absolutely. I think for really testing grid level systems, you need to have a fully functional independent system that can handle it. So yeah, that's an absolutely great point.
So I wanted to, this is your opportunity to stand up and tell us what you think we should be doing in terms of new programs. So we've got a few ideas here, but I really would encourage you to use this time to give us your ideas. I think one comment here is an area that we haven't worked in that is proposed is very high efficiency combustion engines. I think that's actually a great idea. We have not done anything in that area, so I think that's a really good one. Another one we see here is game-changing steam condensation cooling system for power plant water conservation. That's actually going to be one of the topics in the next session that we're having. And so I guess going back to the specific ideas, I think there are some good questions here on that side. One question was to the whole panel is, manufacturability is key, not just proof of concept. And so when you think about the actual commercial deployment and the realistic cost potential of some of these program areas, is this an area you're considering, and what are some of the considerations that you have to put into place in these programs to do that?
I guess I'll just make a quick comment. We're in the early stages, but at all points we're at least trying to make sure that there is a pathway. We also have an excellent commercialization team at ARPA-E, which helps us think through whether or not it makes sense economically that these things could be produced. And one of the things we like to think about a lot is learning curves, which is the idea that how are the cost reductions going to benefit you when it gets to scale, and what scale could it possibly get to? So it's constantly on our minds, but kind of the stage where we start at is this even possible? So we're thinking about it, but I don't think we've done the amount of diligence which is proper before moving forward.
And I'll add on that these are all potential projects, because these are things we're thinking about that we've kind of initially started on. They still have to go through every part of ARPA-E and the team and review before I think they even move on to the next step. But it's always the cost is always, I think, a key thing, but not necessarily as much when we're just thinking about the basic ideas.
Great. At the microphone on the left.
Eric Walks from the University of Maryland. You've mentioned rapid EV charging, and I know there's a big focus for electrification of vehicles. The other aspect which was brought up was high-efficiency combustion engines. But rather than limit it to that, why not just look at high-efficiency conversion of conventional or biofuels to electricity for range extenders?
Absolutely.
Okay, I think I'll pose a couple more questions here, or comments on the photobioreactor. There was a comment to consider clear glass foam for bioreactors. Have you considered liquefaction in a geothermal bioreactor? Interesting idea thrown out there.
Those are really interesting ideas. Those are not things that I had considered, but I'd love to exchange business cards and discuss further. So if you're interested, please come find me.
Great. Comment from the audience? Yeah.
My name is Adrian Bozone from ZNano. We do efficient membranes for osmotic power generation. And I'd like to see more around osmotic power generation, so using salinity difference between river water and seawater to generate power. I think there's a huge opportunity there, both in terms of power generation, like in areas like Alaska where you use fresh water, and then also for tertiary treatment for wastewater treatment plants. So,
how big do you see the total resource being for that?
The estimate is 16,000 terawatt hours per year, which I think comes into about 2% of global energy consumption.
Okay.
So
right here.
Hi, Andrew Day from Days Energy Systems. I wondered if you've considered small-scale natural gas to liquid fuels that would be used on stranded wells. Right now, about 40% of the wells in the lower 48 are stranded. And right now, when we convert natural gas to gasoline and diesel, traditionally we exhaust about half the natural gas or burn it in powering the process, and we convert about half the natural gas to gasoline and diesel. There are some technologies that we've been working on that convert almost all the natural gas to diesel and gasoline, and are scalable, so you can bring them down to the stranded wells throughout the country. And at that point, you can transport them in traditional manners as a cleaner, in terms of greenhouse gases, and cleaner in terms of smog pollution, and use a trapped resource.
That's an area that we're very interested in. ARPA-E recently held a workshop on natural gas conversion, and it's still, in the internal vetting process and trying to carve out the white space. But thank you.
Well, great. We have a whole bunch of good ideas here. I'm going to make sure that these all get to the relevant parties up here. But I think that if that's it, I think we'll let you go a little early here. It'll give you a little bit extra time to network. Each of the fellows will be here out up front, ready to speak with you. And to let you know, the next Emerging Ideas session is going to cover big ideas in renewable energy forecasting, new ideas in real-time electricity pricing, low or no water power plant cooling, and ultra-high efficiency solar. So we will be on a break until, I believe, 10:30, and we'll be reconvening here, and there are also other sessions in parallel that are in your program. So thank you very much.